So the problem that I have just mentioned is formally referred as set membership query problem. Okay, so are you able to see the screen in which I'm writing down?
Yes, sir.
Okay, so I'll just formally state the problem. The problem statement is we have given a universe and some subset of universe. So in case of the example that I have mentioned, our universe is set of all possible URLs, right? So is given a set S of universe U such that S is subset of U with S has say an element, say x1 to xn. Our aim is to construct a data structure that answers the queries of the following form. Basically is y belongs to S, right? So basically we have given a universe and the elements in which we are interested in is some subset of that universe. And our aim is to construct a data structure which basically succinctly represent that set S in some manner, so that when we have a new element, say y, we should be able to quickly and efficiently and quickly and correctly answer whether y belongs to S or not. So in case of the URL example that I have mentioned, our universe U is set of all possible URLs, and set S is the set of URLs that we have visited so far, right? So based on the S, we should prepare a data structure which correctly and efficiently identify whether a new URL we have already visited or not, right? So is the problem statement and the setting is clear?
Yes, sir.
Yes, sir.
Anyone with me? Everyone with me? Okay. So what could be the simple or naive approach for the problem? So basically what we'll do now, we'll just try to see some kind of very simple solution for this problem. And then we'll see what are the limitations of those solutions and how to improve upon, right? So see some. So can any one of you suggest some simple solution for this problem?
Maintain a list of all URLs you visited and check for every link that is shown on the page.
Yes. And how to maintain that list of URL?
Maybe a file in on your disk.
Okay. Okay. So for simplicity, we can assume that there is a mapping which maps these URLs to one unique integers, right? So we can assume that. So we assume that there exists a mapping that maps URLs to unique integers, right? So without loss of generality, we can assume that these S consist of integers, right? So now can you tell me your solution? So now essentially we need to store some numbers, integer numbers. So we are just simplifying the problem.
Probably we can maintain a hash data structure and hash these numbers. And in the second set, we can look for that corresponding hash is present or not.
Yes, so that will be our kind of improved solution. So that we'll see. So first, maybe some simple solution we'll see based on say binary search tree and bit vector. So yes, so hash is the final ultimate hash based solution is the final that we'll look upon.
Okay. Then
Sorry.
Then probably we can maintain it in a list and search in a linear time complexity.
Yes. Yeah, so list approach is one solution. We can also make a binary search tree, and similarly we can make one bit vector type of data structure. Okay, so I'll just list down two of them based on bit vector and binary search tree, and of course we can do the keep them in list and do the linear search as well. So in bit vector thing, what we do, we just maintain an array of we just maintain a binary array. So suppose and its size is size of our universe. Right? So suppose these are the positions. 5, 6, 7, 8. So suppose our size of universe is 10, so we make a 10 size array, and suppose in S, our set S, we have elements, say for example 1, 4, and 9. So what we'll do, we'll just mark the corresponding position as 1, 4, and 9, and remaining as 0. Right? Basically, in this bit vector approach, what we do, there is one bit for each possible elements of U, and we set basically mark 1 the corresponding bits present in S, right? So this is basically very simple solution, but can you just tell me what will be the search time? So suppose if we get a new element, say Y, and if we need to check whether Y was present in S or not, what do we need to do? We just need to probe the corresponding position. So suppose say Y is 9. So we just need to look at the corresponding position. If that position is 1, we'll just say that Y belongs to S. Right? So what will be the search time?
It's unit times.
It's constant. Right? And what is the space complexity? Basically we need to maintain an array of size of U.
Universe.
Right? The size of universe. Right? So this will require order of size of U many bits. So is this part clear to everyone? right?
Sir, why would be the search time be constant? Like we have to search the whole array to find whether it's present
No,
or
no.
not, right?
So, okay, so our algorithm is, so suppose basically we just mark the corresponding position as 1. So suppose in our set we have 1, 4, and 9. So we just marked 1, 4, and 9 as 1 and remaining as 0.
Oh, okay, in terms of indexing. Okay.
So we just need to go in the particular index and see if that value is 0 or 1. Right? So we don't need to search in linear fashion. We can just directly go to the corresponding index and see whether that value is 1 or 0.
Yeah, got it.
Okay. Okay. So, and the another approach is could be based on, say, binary search tree. Right. Again, so what we can do, we can just make a binary search tree. On the elements of S, right? And we can do the search based on usually using the usual binary search algorithm. Right. So what will be the search time? And here I'm assuming in our set S, we have n elements. So basically we need to focus on two things, search time and space complexity. Right. So essentially we'll just make binary search tree for the element of S. Right. So what will be the search time?
Log of n.
Log n.
Yeah. So it is order of log n. And what will be the space complexity? Basically, what is the space required to store this binary search tree?
Same.
Not really. So say U is our universe. So, and essentially we are assuming that for simplicity, we map each element to one of to integer. To store a number from 1 to bar of U, we require how many bits? Log of U, right? And since there are n element in S, so the space complexity will be order of n log size of U. So is this part clear?
No, sir.
Okay. So so we are assuming for simplicity that our universe consists of elements, integer valued numbers, right? To store an integer value number, say x, how many bits do we require?
Log x.
Log x. And since our universe, size of universe is this bar of U, to store a number from this universe will require log of this much size, right? And there are n elements in our set S. To store everything will require n log of size of U. Right? So is it clear now?
Okay, got it. Yeah. Actually, in the previous example, actually S is not defined. Like we can also do the same thing in the previous example also, right? Order of n instead of whole universe, we can keep only S element in the array instead of keeping. Oh, okay, I got it. So we are not sure whether it will be in 1 to n. It can come randomly.
Yes, yes.
Okay.
It could be any element from the universe, right? So we require a bit array of size of universe, not size of S. Okay. So now let's try to compare these two algorithms. So we have binary search tree and we have bit vector. Okay. So in binary search tree, the search time for binary search tree is order of log n, whereas the search time for bit vector is constant. And the space complexity for binary search tree is order of n log of size of u, whereas for bit vector it's order of log of u. So in binary search tree, the space complexity is less, but the search time is large. Whereas in bit vector, its search is very fast in constant time, but its space complexity is linear in the size of universe. So the space complexity in bit vector is linear in the size of universe, whereas in the binary search tree, it's logarithmic in the size of universe. Right. So ideally, we would like to keep best of both worlds. Basically, we want our search to be as good as say constant time search, and the space complexity which has say logarithmic or maybe better dependency than this over the size of universe, right? So we, in a way, we would like to come up with a data structure that gives constant time search and somewhat very space efficient, right? So is the motivation clear now?
Yes, sir.
Okay. So in fact, we get this improvement by using the technique from universal hash function. And but there is some trade-off. So if we want to get uh, like constant time search algorithm, and which is also very space efficient, then we may have to give up something on the accuracy, right? And that thing is captured by false positive thing. Okay, so I'll just elaborate what false positive means. So basically, to obtain speed and space efficiency, what we do, we allow some error, right? Which is, and we also quantify that our error is small. And the error is quantified by false positive. Basically, suppose our query item Y, it was not part of our set S, but we may report that Y belongs to S, right? So essentially, that element was not present in the set, but we incorrectly report that Y was present in the set. But we'll make sure that probability of false positive is very small. Right. So is the motivation clear now? basically the setup and what do we need to achieve.
Yes, sir.
Okay, so I hope in the class we have covered universal hash functions. So I'll just quickly recall it so that we all remain on the same page. Okay. So our notation is U is universe of these, and suppose M is the number of slots. Yeah. So essentially you can think of, we have M bins and so there is a hash function that takes the keys or the element of the universe and randomly assign it to one of these M positions. Right? So this hash function H that maps element from one to 0 to M minus 1. So we call a family of hash functions H that which is set of this type of hash functions that takes the element from the universe and map it to one of these M slots is called universal family. If we take two elements from the universe for all X and Y belongs to universe such that X is not same as Y, then probability that both X and Y maps to the same bin is at most 1 upon M, right? Probability that Hx is equal to Hy is at most 1 upon M, and where probability is over the choice of functions. Right. So basically the idea is H is, so the capital H is a family of hash functions based on the small h, and each of this small h maps the element of the universe to one of these slots from 0 to M minus 1 bins uniformly. And the constraint is that if we choose a random hash functions, this small h from this capital H family of hash function, then for any two elements of the universe which are not same, probability that they map to the same location in the bins is at most 1 upon M. Right? So is the definition clear? Please let me know if you have any doubt on the statement of this. Okay. And if this is clear, so can you just give me one explicit example of universal hash functions? So there is one universal hash family. So we denote it as HAB. So what we do, we choose two numbers A and B uniformly at random from the universe, 0 to bar of u minus 1. And our hash function is HAB K is, so basically K is the ellipse key which we need to hash, and AB are two random numbers that we have chosen from 0 to size of u minus 1. And our hash function is AK plus B mod P mod M, right? Where P is a prime greater than M. If P is a prime number greater than M. Now, what is the size space required to store this? And it can be shown that this this hash function H, this hash family H is universal hash family, right? And the space required to store this hash function is, so essentially this hash function is what? To store a hash function is nothing but storing these two numbers A and B, right? And storing two numbers A and B would require how much space? And we are choosing that number from 0 to size of u minus 1, right? So this will require order of log of what?
U minus 1.
Or size of u. Right?
Yeah.
Okay. So essentially, store like to store a hash function is same as storing these two numbers A and B. Right. So I hope this part is clear. Now, based on that, we'll just try to come up with an data structure that solves our set membership problem.
Sir, why log?
Sorry? I did not get your question. Can you just repeat?
Writing.
I'm not able to hear you. Can you just repeat your question, please?
Yeah, why it is log, sir? Why it is log of u?
To store, suppose if you want to store a number x, how many bits do you require? Log of x, right?
Okay.
So here we want to store a number, say from 0 to u minus size of u minus 1. So that would require space at most log of size of u.
Thank you.
What are the possible values of m here?
Okay, m is given by the user, right? So basically, m is the number of slots in which we want to hash. So that we know a priori. Right?
Is m a prime number?
M need not to be prime number.
Sir, in our example of the URLs, how do
Yes.
we, is M fixed for all time?
Yes, so basically the M will be your size of your data structure, right? So that you or user need to decide, okay, I cannot spend more than this many bits for our data structure. So the size of that data structure is given by the user, or so that is known to us, and based on that we'll choose the remaining parameters.
Okay, sir.
Right, so suppose if your m is very small, then we'll choose other parameter, and then finally our statement will be that, okay, so you cannot give me more than this m many bits. Then basically these are the parameters that you need to choose, and your false positive will be at most this much. Something of this sort we need to provide.
Okay, so the relationship between false positives and M is inverse. So
Yeah, so that we'll see.
okay,
And intuitively, if m is say very small, then the false positive will be large, right?
Yeah.
So you cannot have both,
yeah,
right?
yeah. Okay. Okay.
Okay, so I hope this idea of universal hash function is clear. So based on that, we'll just go towards the solution of this problem. And this solution is very simple, and it's used in practice quite a lot. And this data structure is called Bloom filter. Have you heard about this term before, Bloom filter? And it's very classical algorithm, and it was discovered by Burton Howard Bloom in 1970s. Okay. Again, our setting is we have universe U and our set of elements, which are subset of U, and the number of elements in set S is n. Right? And our Bloom filter is nothing but a bit array, right? Of say certain size. So what we need to do, we need to maintain an array of m bits. This array is called Bloom filter only. And we initially set to 0.
So all the array elements are set to 0, is it?
Initially, yeah.
Okay.
Okay. And this array is nothing but our Bloom filter. And based on the element of S, we need to update the entries of this array A. And basically, we just need to turn them from 0 to 1. Okay. And what we do, we choose.
How do we choose M?
M is given to us. So this we assume.
Okay, sir.
Okay, so basically, so suppose if you need to build a data structure, and which there you cannot afford to take too much of memory, then basically the requirement of M is given from the user side. And then we choose K hash function. H1, H2 to HK. And that is from universal hash functions. The element from 1 to M or 0 to M minus 1. And how to choose K, that we'll see later. Right? So here we assume that N is given to us and M is given to us, and we need to choose K carefully so that the false positive rate is minimized. And then we'll also give a bound on the number, like the false positives. Right. So is the setting clear?
Yes, sir.
Okay.
We are going to use only one hash function, right, sir?
No, we are using k hash functions, h1 to hk.
Oh,
And we have only one bit array.
okay.
Okay. So now we need to see how do we how do we update this Bloom filter when we see an element in the set S. And once we have updated the Bloom filter upon looking at all the elements of the S, how to perform query. So these two things we will see. So to insert an element, say X belongs to S in the Bloom filter, what we need to do, we need to set few bits, right? Set bits. So basically, we'll compute h1x, we'll compute h2x, so on hkx, right? So these will be some numbers from 1 to m, right? So the output of these hash functions will be some number from 1 to m, and we'll just update the corresponding position in the array by 1. Right? So fairly simple. And if one was already there, then we don't do anything. So is the insert part is clear, and this will do for all the element present in the set S. So is this part clear? Okay, so now the second thing is to answer a query.
Unlike beat vector and BST, so this is not determinate, right?
This is not deterministic because these hash functions are randomized.
But
Right?
this will be used for the same problem, right? A set membership query problem. That's what you.
Yes. So the randomness in this process comes from this h1 to hk. So these hash functions and these hash functions are randomized, and they are randomly sampled from universal hash functions. So for example, in this hash say this is one example of hash family. So from this hash family, we need to choose k hash functions, and choosing k hash function are essentially randomly sampling these numbers a1, b1, a2, b2, and so on. Once we have choose this hash function, then the remaining process is deterministic. Right? So is this part clear?
For every x,
Sir,
are we going to evaluate the hash function, all the hash functions?
Yes, yes. So for every x, right? So for every x, we'll calculate h1x, h2x, hkx, and whatever value we get, we'll just update the corresponding index by 1 in the bit array. And we'll see this by one small example.
sir, one more question.
Huh.
While choosing the hash function, right? So, for example, if is h1 and h2 both are like ax plus b mod 2, sorry, mod k mod m, or h1 and h2 are different?
They are different. So for h1, we need to choose number a1 and b1. And for h2, we need to choose different a2 and b2.
Okay, and still compute the same a1 mod b.
Yeah,
That
so
one.
their
Okay, A1x
their
mod.
algorithm is a1x plus B1 mod P.
Okay.
For this,
Okay.
2x plus B2.
Sir, P will be the prime number of all the A1 A's and
And yeah. Yeah, so P is a prime number.
prime number can be any prime number. It can't be any prime number.
It is a randomly chosen prime number greater than M.
Okay, sir.
Okay, so now to answer a query of the type whether Y belongs to S, again, can you guess the algorithm, the process? Basically, we need to check whether
All the hash functions and
all the corresponding positions are 1, right? So we'll just evaluate Y on all these H1, H2, and HK, and if all of them are 1, we'll just report that Y was present in the S. Otherwise, it was not present in the set, right? So we'll check whether A HI Y is equal to 1 for all I from 1 to K, right? And if our answer is yes, we'll just report that Y was present in and S, and if answer is no, we'll just report Y was not present in S. Okay, so is the algorithm clear? Okay, so I'll just trace the example on very small example, and the algorithm on very small example, and we'll see. Hopefully it will be clear. So for our example, we choose MS10 and KS3. So basically we'll have 3 hash functions, H1, H2, H3, and our size of array is 10. So suppose we need to insert, say, 2 elements, say X1 and X2. And suppose H1, X1, H2, X2, and H3, X3, they are, for example, 1, 4, and 9, right? So okay, so initially it was all 0, and we just mark 1, 4, and 9 as 1, 1, 4, and 9 as 1, and remaining was 0. Right, so initially all of them were 1, and after insertion of X1, we'll just mark these position as 1. Right, so this will be our Bloom filter after insertion of X1, right? And suppose so this is insert X1, and suppose X2 is such that H1 of X2, H2 of X2, and H3 of X2 is maybe 4, 5, and 8. 4, 5, and 8. Right, so here I'm just using different colors. So 4 is already 1, so we don't do anything. 5 was not 1, so we'll just update 5 by 1. and 8 will just update by 1, right? So this is after inserting x2, right? So this is the final snapshot after inserting x1 and x2.
Sir, in the first H1, all should be X1, right? X1 of X1, the 1491. X1 of
Oh,
X1.
sorry. Yeah, thanks for pointing it out. Yeah, my mistake. It is x1. Yes, thank you. Yeah, this is h2 of x1 and h3 of x1. Thank you. Okay, so now suppose we need to query y. There's some y1, and suppose y1 is such that h1 y1, h2 y1, and h3 y1. Suppose these values are say 2, 4, and 8. So we'll just look at 2, 4, and 8. So at this position we have 0. So we'll report y doesn't belongs to say s. Right. So our s is x1 and x2. Okay. So we'll report that y doesn't belong to our set S. Suppose we have to query say another element say y2 such that h2 of h1 y2, h2 y2, and h3 y2 is, for example, 1, 5, and 8. So 1 is present, 5 we have 1, and on 8 we have 1. So here we have to report that y belongs to S, and this will be one of the false positive. Right. So although y2 was, this is y1, this is y2. Although y2 was not present in the set S, but its value is 1 for all these hi of y2s. So we have to report that y2 is present in the set, which will be incorrect. And these are the false positives. So basically our aim is to choose our parameters such that this false positives is minimized. So is this part clear to everyone?
Parameters in the sense A1, B1, A2, B2, A3, B3.
No. So
Hash
here
functions.
here the parameter is the only parameter is the number of hash functions.
Okay.
Yeah, hash functions.
So then how do we from where do we get A1, B1?
Yeah. So m is given to us, m is fixed, n is given to us. So basically k we need to choose carefully so that this false positive is minimized. Okay. So now
Also the formula of the hash function is also something that we have to decide, right?
formula means which formula? This
Like yeah,
Ax plus b mod.
ax plus
A
b
mod.
plus mod into mod b.
No, so here basically we need to choose hash functions, universal hash function, and this is one example of universal hash functions. So suppose if we need to choose k hash functions, then we just need to sample a1, ai, bi, k many times.
Yep, but the type of hash function that we choose will also like be dependent as to how many hash collisions will be there, right?
No. So basically, uh, so here the hash function that we are choosing, they are from universal hash functions. So this I should, I think, choose K hash functions from universal hash family. Right. So here it is fixed that these HIs from universal hash family. And this is one of the example of universal hash functions. There could be other. You are free to choose any other hash function from different universal hash family. And this is one of the example. And all of the universal hash functions satisfy this property.
Okay, so it doesn't matter which universal hash function we choose, like the algorithm will work.
As long as those hash functions satisfying this property, we are good. And this is one of the example of the hash functions which satisfy this property.
Okay.
So now okay, so at least algorithm part is clear. Algorithm part is nothing but creating an array of size m and updating these, calculate the hash values of the elements of the S and update the value from 0 to 1. And to query, we just need to again evaluate the hash function on the query item and check if the all bits was present or not. So algorithm is straightforward, insertion and query. So the only part is remaining is to choose what value of k should we choose given and nm, right? So I hope the algorithm is clear to everyone now.
Yes.
Okay. So now what we'll do, we'll just try to first come up an expression for false positive, and then we'll see how to choose this parameter k so that this false positive is minimized. And in the analysis, we'll use high school level calculus, nothing more than that. Okay. Okay, so okay, we'll just first calculate one expression. So suppose once all the element of S are mapped to or hashed to the Bloom filter, then what is the probability that a specific bit is still 0 after all elements of S has been hashed to? When I say hashed, I mean that I calculated the corresponding hash values and update the corresponding entries by 1. Right? So this term I'm finding as hashed to a Bloom filter, then the probability that a specific bit is still 0. Is what?
By U.
Sorry?
M by U.
Is it 1 by m to the power of k?
No. Okay, so just let's go over it step by step. This is the only kind of somewhat non-trivial part, and rest of the things are kind of straightforward calculation. Okay, so here how our algorithm is working. So here, suppose this is our m-sized Bloom filter. Okay. And we need to map these elements x1 to xn. So what we are doing, we are taking x1 and it just randomly map. So our hash function h1, it randomly maps to one of these positions, right? So suppose x1 maps, h1 maps to x1 to this position. So this position is now updated from 0 to 1, right? So similarly, h2 again takes x1 and maps it to randomly to one of these positions. Suppose that position is 1, this is 1, right? So what is the probability that a particular bit is set, right? It's 1 upon m. So basically, suppose due to h1, what is the probability that x1 mapped to some particular bit and that bit is set now due to h1? That is 1 upon m, right?
Yes.
Because h1 is randomly mapping x1 to some particular bit. And what is the probability that that particular bit is still 0? That is 1 minus 1 upon m, right?
Yeah.
Okay. And now we are hashing this x1 how many times? K times, using k different hash functions.
Yeah.
And that particular bit is still 0, will be what? Raised to power k.
Okay. Yes. Yes.
And how many elements are there? And since we are independently hashing them, this will be kn, right? So is this part clear?
Yes, sir.
Okay. Or I'll just quickly repeat it. So 1 by m is the probability that this a hash function, say h1, sets a particular bit of this Bloom filter due to x1. So that is 1 by m. And that particular bit is unset due to h1, and x1 is 1 minus 1 upon m. And since we are hashing x1 k times using k different hash functions independently, so that particular bit is unset, is raised to power k. And since there are n element to hash and we are independently hashing them, this will be 1 minus 1 upon m raised to power kn, right? So I hope this part is clear to everyone. And this is the only kind of non-trivial part in the analysis of Bloom filter. And we can also approximate it by e raised to power minus kn upon n, right? So this is just a simple approximation. So this is the probability that a particular bit is still 0 after hashing all the elements of S using these hash functions h1 to hk. So, but what is our false positive? That probability that a set of k specific bits are 1, right? So now can you tell me what is the probability of false positive? Probability that a set of k specific bits are 1, right? So in case of this y, these case specific bits were 1, and due to y, due to that we need to report that y2 was false positive, right? So here we have calculated that is probability that a specific bit is 0 is this much, and the probability of false positive is probability that a set of k specific bits are 1. So that probability is, suppose we're denoting that as F. So that probability is nothing but 1 minus P raised to power K. Right? So is this part clear to everyone?
So why are we raising it to K again?
Okay. So this is the probability that a specific bit is still 0, right? So what is the probability that a specific bit is still 1?
Okay,
That will be
okay.
1 minus P, right?
Yeah.
And in order to report a false positive, what we want a set of
All
K
K.
specific bits are 1, right?
So
this
it is
would,
at least one of K is not matching, right?
no, all of them should match. Then only we report.
Say positive. Okay, okay. Yes, yeah.
It is 1 minus P raised to power K. So I hope this is clear to everyone. If not, please ask questions. Okay, so I'll just replace this thing over here. So this is 1 minus e raised to power minus kn upon m raised to power k. Okay. So this is the probability of false positive. So now I have a question. So if we, so just rewrite here, f is 1 minus e raised to power minus kn upon m raised to power k. So here n and mn are given to us. So if we increase the value of k, will the false positive will increase or decrease?
Decrease.
Why decrease? So just note that this k appears here in two positions. One is here. I'm circling one of them as green and other one of as red. So if we increase the value of k, right? So if we focus only on, say, this k, so this is one quantity which is smaller than m, smaller than 1. So this quantity is smaller than 1. And if we increase the power of k to quantity which is smaller than 1, so that quantity will decrease, right? So this will decrease the value of f. Now, but if we look at the other k, now if you look at this k, right? So just ignore for a moment to this k. So this is what? This is 1 minus 1 upon e raised to power kn upon m, right? So if we increase the value of k, this quantity will increase and this quantity will decrease and this quantity will increase, right? So is this part clear? So if you focus on this k, if we increase the value of k and ignore for a minute to this k, so this quantity will increase, this quantity, overall this quantity will decrease and this quantity will increase. So effect of this k, if we increase the value of k, this will increase the value of f. right? So if we see on one, so basically in this expression, k is appearing 2 times. And if we stare one of them individually, by increasing the value of k, the overall quantity can decrease as well as increase, right? So if we just try to plot this expression, we'll get something like this. So this is number of hash functions k, and this is false positive. Right. So now we need to find an optimal value of k on which this false positive rate is minimized. Right. So what should we do? So basically we want to find some value of k like this on which this false positive is minimum. So now we have this expression f. We need to choose an optimal value of k such that this expression is minimized. So which technique shall we use?
Gradient should be 0.
Differential to 0.
Yeah, so basically it's our high school calculus maxima minima thing. Right? So we'll just differentiate this function by k and equate it to 0 and calculate the value of k, and then double differentiate and see whether it attains minimum or not. Right? So it's fairly simple. So just for ease of analysis, I'll just rewrite this as exponential of k log base e 1 minus e raised to power kn. Right, so this is basically same way to rewrite this thing. And so since exponential is also monotonic function, so I instead can use this function as g. And now f and g are monotonic, so maximizing f is essentially maximizing g and vice versa. So we'll work on, for ease of the calculation, we'll just work on g. And if you want, you can also work on f. We'll finally get the same result. Right, so we'll work on g, which is k log 1 minus e raised to power minus kn upon m. Okay. So we'll calculate del g upon del k, and we'll get log of 1 minus, so basically, so minus kn upon m plus, so this, we differentiate this term and this is remain intact, and now k into, we need to differentiate this log wala term with respect to k, and we'll get kn upon m e raised to power minus kn upon m upon 1 minus e raised to power minus kn upon m. So this you can verify. And now we need to choose equate del g by del k is equal to 0 when k is m upon n log base 2, log 2 base e. That you can just verify it by putting this value of k in this expression, and it will be equated to 0. And can also verify that del square, its double differentiation square is, means that we attain global minimum. right? So finally, this is the value of k that we want. Log base. So basically, given n and budget for m, right? We can compute the appropriate value of k such that, which is this, that false positive is minimized. Right? So is this part clear to everyone? And these are just high school level calculations. So we just come up with an expression of f, which is expression of false positive, and then we differentiate that expression with respect to k and equate it to 0, and this the value of k we got, and then we can verify that if we double differentiate it on this value of k, it's positive, which means that on this value of k we get a global minimum. Basically, if we choose this value of k, then our false positive rate is minimized.
Sir, here we see that it is k is inversely proportional to n.
Okay.
I mean, intuitively, if we have more websites visited, we need less number of hash functions. Is that correct? I mean,
So we should see it both with respect to m and n. So suppose if n is large and m is also very large, then accordingly we can choose the value of k. So I'm not sure if we focus only on one, then we may get the correct interpretation.
okay. So over time, there is possibility of more false positives, right?
Yes.
Okay, sir.
And I started with one of the application of Bloom filter, and essentially it is some kind of modified version or enhanced version of Bloom filter is used in our web browsing device to identify whether a URL we have already visited or not. But this Bloom filter is used in several other very common application, and I'll just try to list a couple of them. So this blogging platform like Medium use Bloom filter to avoid recommending article that we have already that a user have already read previously. Use filter to avoid is that a user have is already read. And this Chrome is also used Bloom filter to identify and block malicious URLs. Chrome use Bloom filter to and several web crawling web crawling applications use Bloom filter to identify if an URL has been a web page corresponding to particular URL has been already been downloaded. So do you know what is web crawler? So
Yes, sir.
so in that case, so web crawler is essentially like, suppose if we want to dump say some web page and there are several hyperlinks in all of these web pages, and we just don't want to basically save a particular web page more than once. So just to identify whether we have saved a particular web page, this web crawler application used Bloom filter to mark if a particular web page has already been downloaded. So,
Sir, how to identify malicious URL?
That I'm not sure. So they may have some kind of classification algorithm to identify it. But once they have identified it, they just mark the corresponding thing as you in Bloom filter, just to quickly check if a particular URL is malicious or not. So they may have some classification algorithm, right? So basically the idea is if they have some classifier which get a new URL, they just if that marks it as say malicious URL, and then the corresponding entry is updated on the Bloom filter. So something of that sort could have been.
Okay.
It's being used, I'm guessing. Web crawler, Bloom filter, identify if a web page okay. So these are like some application, but in fact, Bloom filter is used at many places. So far, any question that on whatever we have covered? No.
What is that space and time complexity?
Okay, so here the space complexity is order of m. So here we are assuming that m is given to us, is provided to us by user. So yeah, okay. So yeah, one more thing which I should have stated. So essentially, yes. So space complexity. So space complexity consists of two parts. One is to store this bit array, which is Bloom filter, and this requires order of m space. And other thing that we need to store is k hash functions.
Sir, order of log m or m?
M.
Okay.
K hash functions, we need to store these h1 to hk. And how much space do we require to store them? is
Order of K. Order of
order
K.
of K, and we did so in order to store a hash function, say h1, what we need to store? These a1 and b1, basically on the example that we have covered. And ai and bi are the numbers randomly chosen from 0 to size of u minus 1, right? So it will be k log of size of universe, right? So is this clear? Right, so is this clear to everyone?
Yes, sir.
Okay. And
Time
complexity. For insertion, so basically we have n elements, and each of those n element we need to, for each of these n elements, we need to perform k hash computations. So this will be order of nk, right? And query. So this is basically insertion of all elements. And for query, it will be basically we have given a query item, say y, and based on that we need to evaluate k hash functions h1 to hk. So this will be order of k. Right?
Yes,
I
sir.
hope, yeah, so this is clear, and it's also very easy to implement, right? So we just need to create a bit array of size m, choose k hash functions, and then we just need to update the Bloom filter on the corresponding entries. That's all. So implementation is also very straightforward. So I hope you will be able to implement this Bloom filter.
So one general question.
Yeah.
In the space complexity, we have order of K log universe, right? We generally don't know the universe size, so how do we decide that part?
Okay. So yeah, so that is good question. Yeah, so yeah, so in that case, we need to make some guess, which is kind of not very exact, but somewhat give a good approximation based on the our problem domain.
Okay, sir. So it requires some domain knowledge.
Some domain knowledge, yes.
Okay. Okay. Thank you, sir.
Okay.
So
So
one
yeah,
question is like k is equal to m by n log 2. So that was the proof, right?
yes.
Okay. So basically, if m, like I'm just going back to the same question asked, if n is greater than m, so then that means we are like the false positive will be more, right? Just confirming. If n is greater than m.
So more with, so basically, if you are saying more, then what is more with respect to what?
Meaning, then we will have more wrong results. Or I'm so basically what is happening is like I have m array, and there are numbers coming in, and it is reaching more than m. So there might be a chance that all the k hacks function by that time has set all the bits to 1. So any new number comes in, so it will say that it is existing.
Yes.
So which means it is a False one. Yes,
Yes.
false. Yes, so that's what I just. Okay.
Yes. So generally we take break now in between. So
Yes, sir. 15 minutes generally.
15 minutes. Okay, so I think I'll stop here now and we'll rejoin at say 12:05. Okay, and we'll continue our discussion.
Yep. So you can stop the
Okay, sir.
recording.
So I should